In the previous video, we have seen that the GPS systems will emit signals enabling the computation of Earth-centered Earth-fixed coordinates by using ephemeris file or GPS broadcast ephemeris. So, and as you recall, the GPS system uses the Keplerian parameters formalism to compute the satellite's three-dimensional Cartesian coordinates. Now, let's proceed to GLONASS. We want to give a brief explanation for the GLONASS orbit. We will not make any further computation on that, but you will have the idea how the GLONASS navigation message is structured. So as you can see, this is the Rhinex version, and this includes here the GLONASS. So R denotes here the GLONASS, and you can see this includes some blocks again. So in GPS system, we had 8 lines of information, 8 rows, but here you can see these are 4 rows. So we will now go into the details what these items each mean. So in the header file system, so the time system for the GLONASS to UTC conversion, as you see the polynomial parameters, and these parameters are 0. So this means different from the GPS systems and other GPS Galileo and Beidou systems, GLONASS uses universal time coordinated system UTC system time. So that's why there is no need for the conversion. So and there is also a leap second line here, so the necessary information is included. So in GPS, as said, so the parameters are given in Keplerian parameters, and their temporal variation are also included. So some of the parameters, of course, for example, the argument of perigee, lowercase omega, and the eccentricity value does not change within 2 hours of interval. But here, so this formalism, this Keplerian element formalism, is not used in GLONASS system. So instead of that, the GLONASS system uses another approach. So let's first begin with the first. So this the first column denotes the R system, the GLONASS first satellite, GLONASS 01 satellite number. Again, this time is different from GPS. It's not GPS system time, so it's atomic time interval normally, but here it is UTC time. It is the time interval which you use in our daily life. So there is again here the clock bias. So in the third, you can see the clock bias of the satellite. So it is around 0.04 nearly milliseconds. Now the other components, fourth and fifth components, can be omitted for our use. So now the second line, as you see in the X component, we include the position, the velocity, and the acceleration. So the third, these first 3 elements denote these in this order, and the satellite's position is given in Earth-centered Earth-fixed coordinate. So, but GLONASS uses different ellipsoidal definition and datum. So if we compare to GPS, for example, GPS uses WGS 84 system. So, but GLONASS uses another system. But you see here the satellite position and velocity is given. So this is the initial value problem of the orbital determination problem. So this means if you give uh, the the position and velocity of the satellite, and if you model the acceleration, you can easily compute at the next time t, for example, the satellite's position. And this is in x component. As you see easily, there is no acceleration in the x component. So this may be due to this, okay, this a certain epoch. And in this third line, this satellite position again for y component, velocity and acceleration are also included there. And the fourth line, you see this time the z component. So as you see, a GLONASS system uses the different determination of the orbit. It uses the initial value problem. So, and this orbital information for the GLONASS system will be given every half an hour. So the different again from the GPS system. So the orbital information of the satellites will be updated every half an hour. So in GPS system, the orbital information is valid for 2 hours. So, but in GLONASS it is different. So we can see here, for example, let's have a look to RO1 satellite. So within the file, so let's search for this next position, for example. So here you see at 6:15, okay, 6:15. What is the next? So you see 6:45 and 7:15, and the next will be 7:45, etc. So the orbital information will be included here in the orbital in this initial value problem formalism. For example, you see the third terms here have been zero. Third and fourth terms in our case have been zero, but here, as you see, it depends on the location of the satellite, and this acceleration information is included for that satellite position for R17, for example. So this is the second case. This is the GLONASS case. There are other GNSS systems, for example, European Union's Galileo, Beidou, Chinese system, Japanese system, QZSS. These systems use the same formalism as GPS use. So they use the Keplerian parameters to determine the satellite's position. So that's why we don't give the detailed information about the file structure of the navigation messages for those systems. So again, briefly noting that GPS uses Keplerian style orbital information, and the GLONASS uses the initial value problem, where the satellite's position at a certain time t inter t naught, t0, and the velocity is given, and then you can compute for the next time, of course, by using again the satellite's acceleration at a given time t. And the other systems, European Union, Chinese and Japanese systems, use the GPS-like system. Again, these systems use the Keplerian style of orbital information.